scientists have a really good picture of the very early universe, something we know and love as the Big Bang Theory. In this model, a long time ago, the universe was far smaller, far hotter, and far denser than it is today. In that early inferno 13.8 billion years ago, all the elements that make us what we are were formed in the span of about a dozen minutes. Even earlier, this thinking goes, at some point our entire universe, all the stars, all the galaxies, all the everything, was the size of a peach and had a temperature of over a quadrillion degrees. Amazingly, this fantastical story holds up to all current observations. Astronomers have done everything from observing the leftover electromagnetic radiation from the young universe to measuring the abundance of the lightest elements and found that they all line up with what the Big Bang predicts. As far as we can tell, this is an accurate portrait of our early universe. But as good as it is, we know that the Big Bang picture is not complete. There's a puzzle piece missing, and that piece is the earliest moments of the universe itself. What came before the Big Bang? It's the question that always comes up when thinking about the origin of the universe. Most scientists simply ignore the question, as it seems to be too hard a nut to crack. But now, in a bold revelation, physicist and professor of particle physics, Brian Cox declared that he strongly suspected that the universe existed before the Big Bang, throwing the theory of our origins on its head.
Well, we used to think that the universe emerged in that state, very hot and very dense at the beginning of time. And we used to call that the Big Bang. But now we strongly suspect that the universe existed before that. And in that sense, it's possible to speak of a time before the Big Bang.
Join us as we dig deep into how Brian Cox debunks the Big Bang with the creation story that came before the existence of the universe. The idea of the Big Bang first came about back in the 1920s and 1930s. When we looked out at distant galaxies, we discovered something peculiar. The farther away from us they were, the faster they appeared to be receding from us. According to the predictions of Einstein's general relativity, a static universe would be gravitationally unstable. Everything needed to either be moving away from one another or collapsing towards one another if the fabric of space obeyed his laws. The observation of this apparent recession taught us that the universe was expanding today. And if things are getting farther apart as time goes on, it means they were closer together in the distant past. An expanding universe doesn't just mean that things get farther apart as time goes on. It also means that the light existing in the universe stretches in wavelength as we travel forward in time. Since wavelength determines energy, shorter is more energetic. That means the universe cools as we age, and hence things were hotter in the past. Extrapolate this back far enough, and you'll come to a time where everything was so hot that not even neutral atoms could form. If this picture were correct, we should see a leftover glow of radiation today, in all directions, that had cooled to just a few degrees above absolute zero. The discovery of this cosmic microwave background in 1964 by Arno Penzias and Robert Wilson was a breathtaking confirmation of the Big Bang. It's tempting, therefore, to keep extrapolating backwards in time to when the universe was even hotter, denser, and more compact. If you continue to go back, you'll find a time where it was too hot to form atomic nuclei, where the radiation was so hot that any bound protons and neutrons would be blasted apart. A time where matter and antimatter pairs could spontaneously form, as the universe is so energetic that pairs of particles, antiparticles, can spontaneously be created. A time where individual protons and neutrons break down into a quark-gluon plasma, as the temperatures and densities are so high that the universe becomes denser than the inside of an atomic nucleus. And finally, a time where the density and temperature rise to infinite values, as all the matter and energy in the universe are contained within a single point, a singularity. This very final point, This singularity that represents where the laws of physics break down also is understood to represent the origin of space and time. This was the ultimate idea of the Big Bang. Of course, everything except that last point has been confirmed to be true. We've created quark-gluon plasmas in the lab. We've created matter-antimatter pairs. We've done the calculations for which light elements should form and in what abundances during the early stages of the universe, made the measurements, and found that they match with the Big Bang's predictions. Coming forward even farther, we've measured the fluctuations in the cosmic microwave background and seen how gravitationally bound structures like stars and galaxies form and grow. Everywhere we look, we find a tremendous agreement between theory and observation. The Big Bang looks like a winner. Except, that is, in a few regards. 3 specific things you would expect from the Big Bang didn't happen. First, the universe doesn't have different temperatures in different directions, even though an area billions of light years away in one direction never had time, since the Big Bang, to interact with or exchange information with an area billions of light years in the opposite direction. Second, the universe doesn't have a measurable spatial curvature that's different from zero, even though a universe that's perfectly spatially flat requires a perfect balance between the initial expansion and the matter and radiation density. And last, the universe doesn't have any leftover ultra-high energy relics from the earliest times, even though the temperatures that would create these relics should have existed if the universe were arbitrarily hot. Theorists thinking about these problems started thinking of alternatives to a singularity to the Big Bang, and rather of what could recreate that hot, dense, expanding, cooling state while avoiding these problems. In December of 1979, Alan Guth hit upon a solution. Instead of an arbitrarily hot, dense state, the universe could have begun from a state where there was no matter, no radiation, no antimatter, no neutrinos, and no particles at all. All the energy present in the universe would rather be bound up in the fabric of space itself, a form of vacuum energy which causes the universe to expand at an exponential rate. In this cosmic state, quantum fluctuations would still exist, and so as space expanded, these fluctuations would get stretched across the universe, creating regions with slightly more or slightly less than average energy densities. And finally, when this phase of the universe, this period of inflation, came to an end, that energy would get converted into matter and radiation, creating the hot, dense state synonymous with the Big Bang. This was regarded as a compelling but speculative idea, but there was a way to test it. If we were able to measure the fluctuations in the Big Bang's leftover glow and they exhibited a particular pattern consistent with inflation's predictions, that would be a smoking gun for inflation. Furthermore, those fluctuations would have to be very small in magnitude, small enough that the universe could never have reached the temperatures necessary to create high-energy relics, and much smaller than the temperatures and densities where space and time would appear to emerge from a singularity. In the 1990s, 2000s, and then again in the 2010s, we measured those fluctuations in detail and found exactly that. The conclusion was inescapable. The hot Big Bang definitely happened, but it's not the beginning of the universe. At that time, there is a question that always comes up when thinking about the origin of the universe. What came before? What happened before the Big Bang? And if there was no before, what was the cause of the Big Bang in the first place? Until a few centuries ago, the answer was easy. Some eternal deity set everything in motion. Even Isaac Newton believed that God created the universe some 6,000 years ago. Later, many scientists, including young Albert Einstein, assumed the universe itself to be eternal and everlasting. But now, most scientists simply ignore the question, as it seems to be too hard a nut to crack. In fact, when astronomers talk about the Big Bang, they usually do not refer to the very beginning of the universe, but to the incredibly hot and compact state of the universe in the first couple of minutes of its existence. To some extent, this is because no one has a real clue about the true nature of time, let alone about the beginning of time. British physicist Julian Barber, for one, has argued that time doesn't even exist, except as an illusion in our minds. According to others, including Stephen Hawking, time came into existence together with the universe, rendering the whole concept of the word before meaningless. As such, asking what happened before the Big Bang would be like asking what lies north of the North Pole, or what distance is shorter than zero. Then again, we simply don't know whether or not there was time before the Big Bang. But Professor Brian Cox said that he has a bold idea. Never one to shy away from the big questions, Brian Cox expressed that he's ready to take on the story of the origin of our universe. The physicist investigated the crucial question of our existence, aiming to discover how the universe came to be. He discussed how discoveries of other galaxies have helped us comprehend how we came to be, as well as the technologies utilized along the route, as he looked at the different cutting-edge space missions that have gotten us closer to the answer. And in a world-shattering revelation, Brian Cox argued there was a time before the Big Bang, a time in which the universe did not exist at all. He explored this in his documentary series, Universe, where everything begins and ends, stating that before the launch point of the Big Bang, there was no matter at all. All that existed was space-time and an ocean of energy, almost still, but gently rippling. This place, as he said, should be imagined as a near-still ocean of energy filling the void. It would have had no structures, and the energy in the space would have caused it to stretch violently, something known in space as inflation. Flipping the Bible creation story on its head, Prof. Cox proceeded to explain the science creation story. And the crux of the story is an unimaginably violent expansion, which is known as inflation.
In the beginning, there was an ocean of energy that drove a rapid expansion of space, known as inflation.
There were ripples in the ocean. As inflation ended, the ocean of energy was converted into matter at the Big Bang, and the pattern of the ripples was imprinted into our universe as regions of slightly different density in the hydrogen and helium gas that formed shortly after the Big Bang.
The denser regions of gas collapsed to form the first stars and the first galaxies. And 9 billion years later, a new star formed in the Milky Way, the Sun. The star was joined by 8 planets, including Earth. And nearly 13.8 billion years after it all began, we emerged, blinking into the light. Notably, Brian Cox is not the only one to make such an argument about the beginning of the universe. A remarkable theoretical physics research has revealed a possible window into the very early universe, showing that it may be just the latest iteration of a bang-bounce cycle that has been going on for, well, at least once, and possibly forever. According to the study, the physics that we use to understand the early universe, a wonderfully complicated mishmash of general relativity and high-energy particle physics, can take us only so far before breaking down. As we try to push deeper and deeper into the first moments of our cosmos, the math gets harder and harder to solve, all the way to the point where it just quits. The main sign that we have terrain yet to be explored is the presence of a singularity, or a point of infinite density, at the beginning of the Big Bang. Taken at face value, this tells us that at one point, the universe was crammed into an infinitely tiny, infinitely dense point. This is obviously absurd, and what it really tells us is that we need new physics to solve this problem. Our current toolkit just isn't good enough. To save the day, we need some new physics, something that is capable of handling gravity and the other forces, combined at ultra-high energies. And that's exactly what string theory claims to be, a model of physics that is capable of handling gravity and the other forces, combined at ultra-high energies. Which means that string theory claims it can explain the earliest moments of the universe. One of the earliest string theory notions is the ekpyrotic universe, which comes from the Greek word for conflagration, or fire. In this scenario, what we know as the Big Bang was sparked by something else happening before it. The Big Bang was not a beginning, but one part of a larger process. Extending the ekpyrotic concept has led to a theory, again motivated by string theory, called cyclic cosmology. Technically, the idea of the universe continually repeating itself is thousands of years old and predates physics, but string theory gave the idea firm mathematical grounding. The cyclic universe goes about exactly as you might imagine, continually bouncing between big bangs and big crunches, potentially for eternity back in time and for eternity into the future. As cool as this sounds, early versions of the cyclic model had difficulty matching observations, which is a major deal when you're trying to do science and not just telling stories around the campfire. The main hurdle was agreeing with our observations of the cosmic microwave background, the fossil light leftover from when the universe was only 380,000 years old. While we can't see directly past that wall of light, if you start theoretically tinkering with the physics of the infant cosmos, you affect that afterglow light pattern. And so, it seemed that a cyclic universe was a neat but incorrect idea. But the ekpyrotic torch has been kept lit over the years, and a paper published in March 2020 has explored the wrinkles in the mathematics and uncovered some previously missed opportunities. The two physicists who authored the study, Robert Brandenberger and Ziwei Wang, both of McGill University in Canada, found that in the moment of the bounce, when our universe shrinks to an incredibly small point and returns to a Big Bang state, it's possible to line everything up to get the proper observationally tested result. In other words, the complicated, and, admittedly, poorly understood, physics of this critical epoch may indeed allow for a radically revised view of our time and place in the cosmos. But to fully test this model, we'll have to wait for a new generation of cosmology experiments. So, let's wait to break out the ekpyrotic champagne. But note that it's just one of many hypotheses in which our universe is not unique, but part of a possibly infinite multiverse, one way or another. A wild new theory suggests there may be another anti-universe, running backward in time prior to the Big Bang. The idea assumes that the early universe was small, hot, and dense, and so uniform that time looks symmetric going backward and forward. If true, the new theory means that dark matter isn't so mysterious. It's just a new flavor of a ghostly particle called a neutrino that can only exist in this kind of universe. And the theory implies there would be no need for a period of inflation that rapidly expanded the size of the young cosmos soon after the Big Bang. If true, then future experiments to hunt for gravitational waves or to pin down the mass of neutrinos could answer once and for all whether this mirror anti-universe exists. Physicists have identified a set of fundamental symmetries in nature. The three most important symmetries are charge. If you flip the charges of all the particles involved in an interaction to their opposite charge, you'll get the same interaction. Parity. If you look at the mirror image of an interaction, you get the same result. And time. If you run an interaction backward in time, it looks the same. Physical interactions obey most of these symmetries most of the time, which means that there are sometimes violations. But physicists have never observed a violation of a combination of all three symmetries at the same time. If you take every single interaction observed in nature and flip the charges, take the mirror image and run it backward in time, those interactions behave exactly the same. This fundamental symmetry is given a name, CPT symmetry, in which C for charge, P for parity, and T for time. In a paper accepted for publication in the journal Annals of Physics, scientists propose extending this combined symmetry. Usually this symmetry only applies to interactions, the forces and fields that make up the physics of the cosmos. But perhaps, if this is such an incredibly important symmetry, it applies to the whole entire universe itself. In other words, this idea extends this symmetry from applying to just the actors of the universe, forces and fields, to the stage itself, the entire physical object of the universe. We live in an expanding universe. This universe is filled with lots of particles doing lots of interesting things, and the evolution of the universe moves forward in time. If we extend the concept of CPT symmetry to our entire cosmos, then our view of the universe can't be the entire picture. Instead, there must be more. To preserve the CPT symmetry throughout the cosmos, there must be a mirror image cosmos that balances out our own. This cosmos would have all opposite charges than we have, be flipped in the mirror, and run backward in time. Our universe is just one of a twin. Taken together, the two universes obey CPT symmetry. The study researchers next asked what the consequences of such a universe would be. They found many wonderful things. For one, a CPT-respecting universe naturally expands and fills itself with particles, without the need for a long theorized period of rapid expansion known as inflation. While there's a lot of evidence that an event like inflation occurred, the theoretical picture of that event is incredibly fuzzy. It's so fuzzy that there is plenty of room for proposals of viable alternatives. Second, a CPT-respecting universe would add some additional neutrinos to the mix. There are 3 known neutrino flavors: the electron neutrino, muon neutrino, and tau neutrino. Strangely, all 3 of these neutrino flavors are left-handed, referring to the direction of its spin relative to its motion. All other particles known to physics have both left and right-handed varieties, so physicists have long wondered if there are additional right-handed neutrinos. A CPT-respecting universe would demand the existence of at least one right-handed neutrino species. This species would be largely invisible to physics experiments, only ever influencing the rest of the universe through gravity. But an invisible particle that floods the universe and only interacts via gravity sounds a lot like dark matter. The researchers found that the conditions imposed by obeying CPT symmetry would fill our universe with right-handed neutrinos, enough to account for the dark matter. But we would never have access to our twin, the CPT mirror universe, because it exists behind our Big Bang, before the beginning of our cosmos. But that doesn't mean we can't test this idea. The researchers found a few observational consequences of this idea. For one, they predict that the 3 known left-handed neutrino species should all be Majorana particles, which means that they are their own antiparticles, in contrast to normal particles like the electron, which have antimatter counterparts called the positrons. As of now, physicists aren't sure if neutrinos have this property or not. Additionally, they predict that one of the neutrino species should be massless. Currently, physicists can only place upper limits on the neutrino masses. If physicists can ever conclusively measure the neutrino masses, and one of them is indeed massless, that would greatly bolster the idea of a CPT symmetric universe. Lastly, in this model, the event of inflation never occurred. Instead, the universe filled with particles naturally on its own. Physicists believe that inflation shook space-time to such a tremendous degree that it flooded the cosmos with gravitational waves. Many experiments are on the hunt for these primordial gravitational waves, but in a CPT symmetric universe, no such waves should exist. So if those searches for primordial gravitational waves turn up empty, that might be a clue that this CPT mirror universe model is correct. In the end, we have to admit we're ignorant about the true beginning of the universe. And even if we lean towards an eternal multiverse with no real beginning at all, we don't know why there is something, or more to the point, why there is everything, instead of nothing. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.